Good morning. Here's your daily tech briefing for 2020-60820. Today we're covering Java, Apache Kafka, Docker, Kubernetes, Git, Angular, and Cloud, AWS/Azure/GCP, plus the Architect's Corner. Let's get into it. Let's start with a quick look at DripSharp, a project that's been making the rounds on Hacker News. The author built a Java to C hash source converter that leans on artificial intelligence models to translate code automatically. In practice, you feed it a Java file, and the tool runs the code through a large language model that has been fine-tuned on both Java and C hash syntax, then spits out a C hash equivalent. The idea is to give developers a head start when they need to move a codebase from the JVM ecosystem to Net, which can happen for a variety of business reasons. Maybe a company is consolidating services on a Microsoft stack, or they've acquired a product that was originally written in Java and want to integrate it more tightly with existing C hash services. What makes DripSharp interesting isn't just the conversion itself, but how it handles the nuances that usually trip up manual rewrites. For example, Java's Stream API maps to LINQ in C, and the tool tries to preserve those fluent pipelines rather than flattening them into loops. It also attempts to translate Java's checked exceptions into C's unchecked model, inserting comments where human judgment is still required. The author notes that the output is production-ready. You still need to review and test, but the generated code can cut weeks of repetitive work down to a few days. For a backend team that's juggling multiple services, that time savings can be a real win, especially when you factor in the cost of maintaining two parallel codebases. Switching gears, the latest episode of the Inside Java podcast, episode 67, dives into the practical side of Java's 6-month release cadence. Since JDK 10 rolled out in March 2018, Oracle has been shipping a new feature release every March and September. That rapid pace sounds great for getting the newest language features, but it also raises the question: can an organization realistically keep up? The hosts break down the trade-offs between the regular releases and the long-term support, LTS, versions, which come every 3 years and receive security updates for a longer period. For a DevOps engineer, the cadence matters because each new JDK can introduce changes to the JVM's garbage collector, default TLS settings, or even deprecate APIs that your services rely on. The episode suggests a strategy of release train tracking. Lock your production environments to the most recent LTS, say JDK 21, while using feature branches or staging clusters to experiment with the next non-LTS release. Automated testing pipelines become essential. You'll want to catch any incompatibilities before they hit production. Tools like Maven's version ranges or Gradle's toolchains can help enforce the right JDK version per project, and container images can be rebuilt automatically as new JDK builds appear. In short, whether you're using an AI-driven converter to migrate code or wrestling with Java's fast-forward release schedule, the common thread is automation and careful testing. By integrating these practices into your CI/CD flow, you can stay on the cutting edge without sacrificing stability. Apache Kafka keeps popping up whenever you're planning a data pipeline, and the latest comparison from the RabbitMQ team gives us a fresh look at where Kafka shines and where it might fall short. At its core, Kafka is a distributed log. Think of it as an append-only journal that stores streams of records in order, partitioned across multiple brokers for scalability. Because each partition is an immutable sequence, consumers can replay data from any point, which is a big win for audit trails, event sourcing, or any scenario where you need to reprocess historic events. One of the biggest differences highlighted in the RabbitMQ versus Kafka guide is how the two systems handle message durability. Kafka writes every record to disk immediately and replicates it across a configurable number of brokers. That means even if a whole rack goes down, the data stays safe as long as you've set a replication factor of at least 2. RabbitMQ can also persist messages, but its default mode leans more toward in-memory queues, which can be faster for low-latency request-reply patterns, but less forgiving in a failure scenario. Throughput is another area where Kafka usually pulls ahead. Because it batches writes and uses sequential disk I/O, it can handle millions of messages per second on modest hardware. The comparison notes that RabbitMQ's per message overhead is higher, making it better suited for workloads with complex routing or where you need advanced features like per message TTL, time to live, and dead letter queues. If you're building a microservices architecture that needs to fan out events to many downstream services, Kafka's high-throughput publish-subscribe model and its ability to retain data for days or weeks give you a buffer against downstream hiccups. Consumer semantics also diverge. Kafka's consumer groups let multiple instances share the load of a single logical subscription, with each partition assigned to only one consumer in the group. This guarantees ordered processing per partition and makes scaling out straightforward. RabbitMQ uses a push-based model where messages are delivered to consumers as soon as they're ready, which can reduce latency but requires more careful handling of back pressure. For a DevOps engineer, the operational impact matters. Kafka's reliance on Zookeeper, or the newer Craft mode, adds a dependency you need to monitor, while RabbitMQ's management UI gives you real-time insight into queue depths and consumer health. The guide points out that Kafka's storage model can grow large quickly, so you'll need to plan retention policies and disk capacity. Conversely, RabbitMQ's queues can fill up and start rejecting messages if you don't size them appropriately. In practice, many large-scale services, LinkedIn, Netflix, Uber, choose Kafka for its durability, ordering guarantees, and ability to act as the backbone for event-driven architectures. If your workload is more about reliable point-to-point messaging with complex routing, RabbitMQ still makes sense. The new comparison helps you weigh those trade-offs with concrete numbers, so you can pick the right tool for the job without guessing. Docker just opened up its verified publisher program to a self-serve model, which means anyone building container images can now apply directly through Docker Hub without waiting for a sales or partnership rep to intervene. A verified publisher, or DVP, is essentially a badge that tells developers this image comes from a trusted source, has passed security scans, and follows Docker's best practice guidelines. Until now, getting that badge required a manual outreach process, often involving a back and forth with Docker's business team to prove you're an established vendor or open source maintainer. The new workflow is built into the Docker Hub UI. After you sign in, you'll see a Apply for Verified Publisher button on your organization's page. The form asks for basic details: your organization name, a short description of the software you ship, links to the source repository, and evidence that you maintain a regular release cadence. Docker then runs an automated assessment that checks for things like signed images, vulnerability scanning via Docker scan, and proper use of multi-arch manifests, so the images work on both x86 and ARM hardware. Why does this matter for a backend or DevOps engineer? First, it reduces the time you spend vetting third-party images. When you pull an image tagged with the Verified Publisher badge, you can be more confident it hasn't been tampered with and that the maintainer follows a consistent security patching schedule. That cuts down on the manual checks you'd otherwise have to perform in CI pipelines, like running your own Trivy or Gripe scans on every external image. Second, the self-serve route lowers the barrier for smaller teams and open-source projects to get that visibility. A startup that publishes a Redis-compatible cache layer, for example, can now get the badge quickly, making its image appear higher in search results and more likely to be adopted by other engineers. Docker also promises that verified publishers will get a dedicated support channel and early access to new hub features, such as automated provenance metadata that records exactly how an image was built. In practice, that means if you run into an issue with a verified image, you can reach out through a faster, more direct line rather than posting in generic forums. Overall, the shift to a self-serve application streamlines trust building in the container ecosystem, letting engineers focus more on building services and less on hunting for safe base images. Kubernetes just dropped a handful of new releases, and for anyone running clusters in production, those numbers matter more than they look on the surface. First up, version 1.35.8 landed as the latest patch for the 1.35 series. A patch release like this is essentially a collection of bug fixes, security updates, and small stability tweaks that have been backported into an already supported minor version. The changelog for 135.8 lists a series of issues that were addressed, ranging from scheduler edge cases that could cause pod placement delays to kubelet crashes that were triggered by certain CSI driver responses. For a backend engineer, those kinds of fixes translate directly into fewer unexpected restarts and more predictable resource allocation, especially when you're running high-throughput services that rely on tight latency guarantees. Right alongside that, the 1.36 series got its own patch, version 1.36.4. The 1.36 line is still relatively fresh, having introduced a number of feature graduations in earlier releases, like the stable API for endpoint slices and enhancements to the pod security admission controller. The 1.36.4 patch continues the trend by tightening up the API server's handling of malformed requests and polishing the control plane metrics that you might be scraping with Prometheus. If you've already upgraded to 1.36 to take advantage of those newer APIs, applying the 0.4 patch is a low-risk way to lock down a few lingering edge case bugs that could otherwise surface under heavy load. On the older side of the spectrum, version 1.34.11 is the most recent update for the 1.34 branch. That branch is now in maintenance mode, meaning the Kubernetes community is only issuing critical fixes and security patches. The 1.34.11 release includes a handful of CVE-related patches, common vulnerabilities and exposures that address privilege escalation paths in the Kube API server. Even if you're running a legacy cluster that hasn't moved off 1.34 yet, those patches are essential. Many on-premise environments, especially those that lock in a specific version for compliance reasons, will need to cherry-pick these updates to stay within their security baselines. Finally, the most forward-looking item is version 1.37.0 RC1, the first release candidate for the upcoming 1.37 minor release. A release candidate is essentially a feature-complete snapshot that the community pushes out for broader testing before the final GA, generally available version. The 1.37 RC1 changelog highlights a few big-ticket items that have been in development for a while. The graduated pod-ready-to-start containers feature gate, which gives you finer control over when a pod is considered ready, and a new, graceful node shutdown flow that helps cloud providers drain nodes without dropping in-flight traffic. For a DevOps engineer, those changes can simplify rolling upgrades and reduce the risk of service disruption during node maintenance windows. What does all this mean for your day-to-day workflow? First, keep an eye on the release cadence. The Kubernetes project follows a roughly quarterly minor release rhythm, with patch releases appearing as needed. If you're on a managed service like Amazon EKS, Azure AKS, or Google GKE, the provider will usually roll these patches out automatically, but they often give you a window to test the new binaries in a staging environment before they hit production. If you're self-hosting, you'll need to pull the new binaries from the official release page, update your control plane components, and then roll the kubelet version across your nodes. Because each patch is built to be backward compatible within its minor line, you can typically upgrade one node at a time without draining the entire cluster, which keeps your services up while you apply the fixes. Second, prioritize security patches. The 1.34.11 release, for example, contains fixes for known CVEs that could be exploited to gain elevated privileges inside the cluster. Even if you're not actively using the vulnerable APIs, an attacker could still probe the API server and trigger the flaw. Running a quick kubectl get component statuses. After applying the patch can confirm that the control plane is healthy, and a brief kubectl version check will verify that the new binaries are in place. Lastly, treat the 1.37 RC1 as an invitation to test new functionality early. Spin up a small test cluster, perhaps using Kind, Kubernetes in Docker, or Minikube, and enable the new feature gates to see how they interact with your CI/CD pipelines. That way, when the final 1.37 GA ships a few weeks from now, you'll already have a playbook for rolling it out across your production fleet. In short, the recent releases, 1.35.8, 1.36.4, 1.34.11, and the 1.37 RC1 are a reminder that staying current isn't just about new features. It's about keeping the cluster stable, secure, and ready for the next wave of workload demands. Keep your upgrade plan handy, test the release candidate, and let the chang. On August 17, GitHub experienced a multi-hour outage that knocked out both the public website and the core Git service APIs. The incident was triggered by a cascade of failures in the internal job scheduler that coordinates background tasks such as repository indexing, webhook delivery, and the replication of data across the global storage clusters. When the scheduler hit a deadlock, a situation where two or more processes wait indefinitely for each other to release resources, it stopped dispatching new jobs, and the backlog quickly filled the queues that feed the front-end servers. As a result, users saw 502 bad gateway errors, pull request pages failed to load, and CI pipelines that rely on GitHub's API stalled. GitHub's post-mortem explains that the deadlock was caused by a recent change to the scheduler's lock management code, intended to improve throughput for large organizations. The change unintentionally introduced a race condition. Under high load, two scheduler instances could each acquire a different subset of locks and then wait for the other to release the remaining lock, creating a standstill. Because the scheduler is a single point of coordination for many critical services, the deadlock propagated outward, effectively taking the whole platform offline. In the aftermath, GitHub's engineering team rolled back the offending code and introduced a series of safeguards. First, they added a watchdog timer that detects when a scheduler instance has been idle beyond a threshold and automatically restarts it, preventing a deadlock from persisting. Second, they rewrote the lock acquisition logic to use a hierarchical ordering, which eliminates circular wait conditions, a classic fix for deadlocks. Third, they expanded their load testing suite to simulate the exact traffic spikes that triggered the issue, ensuring future changes are validated against realistic stress scenarios. Beyond the immediate fixes, GitHub announced a longer-term roadmap aimed at increasing overall reliability. This includes migrating some background workloads to a more resilient, distributed task queue built on Apache Kafka, which can tolerate node failures without halting the entire pipeline. They're also adding more granular health checks and real-time alerting for the scheduler, so operators can spot anomalies before they cascade. For a backend or DevOps engineer, the key takeaways are twofold. One, even a seemingly small change in internal orchestration code can ripple out to affect every Git operation you depend on, from cloning repositories to triggering CI jobs. Two, robust lock management and proactive monitoring are essential when building systems that coordinate many moving parts. The incident serves as a reminder to incorporate thorough concurrency testing and to design fail-over mechanisms that keep critical services like Git available, even when a single component misbehaves. The Angular team just pushed a handful of small but meaningful updates across the 22 series, the 21 LTS line, and even the older 20 branch, and they're worth a quick look if you're stitching Angular front ends into your Spring Boot or Liferay DXB backends. First up is the pre-release 22.2.0 Next 3. It's a next version, meaning it's the preview that will become the next stable release once the final testing cycle is done. The changelog is short, but the two fixes it contains touch core parts of the framework that you'll see in everyday code. In the animations package, the team fixed a bug that was causing change detection to miss updates when an object's trigger value was read using the older in operator. The new code now uses object has own instead. Object has own is a built-in method that checks whether a property exists directly on the object, not somewhere up its prototype chain. By switching to that, Angular avoids false positives from inherited properties and reduces the amount of work the change detection engine has to do. In practice, you'll see fewer expression has changed after it was checked, warnings during development, and a tiny performance gain in production because the framework can skip unnecessary checks. The second fix in the same preview lands in the common package, specifically in key value pipe, transform. Key value pipe is the pipe you use when you want to iterate over an object's key value pairs in a template. For example, *ng for equals let entry of my obj key value. Previously, the pipe would widen the type of the keys to just string or number, losing any literal union information you might have defined in your TypeScript model. That forced developers to cast the result back to the exact shape they needed, which defeats the purpose of TypeScript's strict typing. The new change preserves the literal key union, so if you defined an object type like status, open, closed, the pipe now returns that exact union. That means your IDE can catch mismatched keys at compile time, and you spend less time writing defensive code. For a large enterprise app where you have dozens of key value tables, that type safety can prevent subtle bugs from slipping into production. Both of those fixes are also backported to the stable 22.13 release, which is the current recommended version for most production workloads. The backport tells you that the Angular maintainers consider these issues important enough to ship to the current LTS line without waiting for the next major version. If your CI pipeline pins to 22.1x, you'll want to bump the lockfile to 22.13 to pick up the same improvements. The other two releases you'll see are 21.2.21 and 23.29, both of which contain the same change in the platform browser package. They now disallow event handler attributes inside meta tags. In earlier versions, you could write something like meta http equiv equals, refresh content equals 0, URL equals JavaScript, alert 1, onload equals, and the browser would execute the JavaScript. That is a classic vector for cross-site scripting, XSS, attacks, especially in enterprise portals where meta tags are often generated from user-controlled data. By rejecting any attribute that looks like an event handler, attributes that start with on, such as onload or onclick, Angular's rendering engine blocks that attack surface at the framework level. The fix is applied to the 21 LTS line and the older 20 LTS line, which shows a consistent security hardening across the board. If you run a Liferay DXB site that injects meta tags based on configuration data, this change means you no longer need a custom sanitization step for those tags. Angular will throw an error during compilation if you accidentally add an event handler attribute. From an operations perspective, these updates are all backward-compatible bug fixes, so you shouldn't see any breaking changes in your build. However, because they touch the compiler and core pipes, it's a good idea to run your full test suite after pulling the new versions. In a typical CI/CD pipeline, you'll see a small bump in the node module's hash, and the Angular compiler might emit a few additional warnings about deprecated patterns that the new code now flags more strictly. That's a sign you're moving toward a cleaner code base, not a problem. Finally, a quick note on version strategy. Angular's release cadence still follows the 6-month major version schedule, with a long-term support, LTS, branch that receives security and critical bug fixes for 18 months. The fact that the same meta tag hardening appears in both the 20 and 21 branches tells you the team is aligning security fixes across all supported lines, which is reassuring for enterprises that can't upgrade every few months. If you're on a 20x line because of legacy dependencies, you can safely apply 23.29 and get the same protection as newer projects. So to sum up, the next preview 22.2.0 next. 3 gives you a more accurate change detection check and tighter type safety in key value pipes. The stable 22.13 backports those improvements, and the 21.2.21 and 23.29 releases close a subtle XSS hole in meta tags. Updating your package, JSON, running a quick test pass, and committing the lockfile should be all that's needed to reap the benefits. BigQuery just announced a shift in how its graph processing capabilities will be offered. Starting on April 26, 2027, the core graph engine that powers BigQuery Graph will only be available in the Enterprise and Enterprise Plus editions. In plain terms, if you're on the Standard Edition or you've been using on-demand billing for graph workloads, that access will be retired. BigQuery Graph is the feature that lets you run graph-style queries. Think social network traversals, recommendation paths, or fraud detection link analysis, directly on the data warehouse without pulling the data into a separate graph database. Under the hood, it builds a virtual graph from your tables and lets you apply measures like shortest path, PageRank, or community detection using SQL extensions. For many teams, that means you can keep everything in one place, avoid data duplication, and leverage BigQuery's massive scalability. Why does the change matter? First, The enterprise tiers are priced differently. They're subscription-based rather than the per-query, on-demand model many smaller teams rely on. If you've been running occasional graph queries on a standard project, you'll suddenly see those jobs fail once the cutoff date arrives. The error messages will point to unsupported addition for core graph processing, and you'll need to either upgrade your subscription or move the workload elsewhere. From an operational perspective, the upgrade isn't just a billing tweak. Enterprise editions come with additional quotas, higher concurrency limits, and tighter integration with other Google Cloud services like Vertex AI. That can be a benefit if you're already scaling graph analytics, but it also means you'll have to adjust IAM policies, budgeting alerts, and possibly re-architect any automation that provisions BigQuery resources on the fly. If upgrading isn't an option, you have a couple of workarounds. One is to export the relevant tables and load them into a dedicated graph database, such as Neo4j or Amazon Neptune, handling the ETL yourself. Another is to rewrite the logic using classic SQL joins and window functions, though you'll lose the optimized graph algorithms that BigQuery Graph provides. In short, the deprecation forces anyone still on standard or on demand to make a decision. Move to enterprise, re-engineer the workload, or migrate to an external graph solution. It's a good moment to audit your current graph usage, estimate the cost impact of an enterprise upgrade, and plan any necessary migrations well before the April deadline. Now, let's shift gears for the Architect's Corner. 5 minutes on real enterprise software architecture and system design. When IBM set out to push its quantum processing unit from a handful of qubits into the realm of a few hundred, the engineering problem they ran into wasn't just, how do we write better software? It was a full-scale systems design challenge that spanned mechanical engineering, cryogenics, high-frequency electronics, and software control. In plain terms, they needed a way to keep a delicate chip at temperatures colder than outer space, on the order of a few tens of millikelvin, while simultaneously feeding it thousands of control signals, reading out the results, and doing it all in a package that could be replicated in a data center environment. The constraints were brutal. A dilution refrigerator, the workhorse that gets you down to those ultra-low temperatures, has a finite cooling power. Every wire that runs from room temperature down to the quantum chip carries not just the signal you need, but also a tiny amount of heat. Multiply that by the hundreds of control lines required for a modern superconducting qubit array, and you quickly exceed the fridge's ability to stay cold. Add to that the mechanical vibrations from the cryocooler, the electromagnetic interference from the control electronics, and the sheer physical footprint of a system that was originally built for a single-digit qubit experiment. The team's original architecture, room temperature control hardware, a long bundle of coaxial cables, and a monolithic fridge, simply wouldn't scale. What they built was a fundamentally new, hierarchical cryogenic architecture that treats the refrigerator not as a passive cold box, but as an active, modular platform. At the top level, they introduced a cold cartridge concept. Instead of keeping all the control electronics at room temperature, they moved the first stage of signal generation and conditioning down to the 4 Kelvin stage of the fridge. This is where cryogenic CMOS chips, designed to operate reliably at a few Kelvin, sit side by side with the quantum chip. By generating the microwave pulses that drive the qubits right there, they cut the length of high-frequency cabling dramatically, which in turn slashed the thermal load and reduced signal attenuation. Below that, the actual qubit chip lives on the mixing chamber, the coldest part of the system, at roughly 10-20 millikelvin. The team introduced a thermal isolation stack that separates the 4 Kelvin cartridge from the mixing chamber with a series of low conductivity supports and superconducting wiring. Those wires are made of niobium titanium and are carefully routed to minimize both thermal conduction and magnetic flux noise, which can decohere the qubits. The result is a clear separation of concerns. The 4 Kelvin stage handles the bulk of the RF generation, while the mixing chamber focuses purely on preserving quantum coherence. Another key piece of the redesign was a modular dilution refrigerator chassis. Traditional fridges are built as a single, monolithic unit, which makes it hard to upgrade any one part without taking the whole system offline. IBM's new chassis is built from interchangeable modules. Cooling stages, wiring harnesses, and the cold cartridge itself can be swapped out independently. This modularity not only speeds up hardware iteration, but also aligns with the software development lifecycle that enterprise teams are used to. You can roll out a new control chip design, test it in isolation, and then slot it into the existing fridge without re-engineering the entire thermal plant. On the software side, the architecture forced a rethinking of the control stack. The low latency, on-chip pulse generation meant that the higher-level orchestration software could now treat the quantum processor more like a classical accelerator. Instead of streaming individual gate instructions over a slow, noisy link, the software compiles a batch of pulses, uploads it to the cryogenic chip, and lets the hardware execute the sequence autonomously. This burst mode execution reduces the round-trip time from microseconds to nanoseconds and frees up the host CPU to handle more parallel workloads, something that resonates strongly with enterprise patterns for offloading compute to specialized hardware. Why does this matter for a software architect working on large-scale enterprise systems? First, it's a vivid illustration of the trade-off between moving functionality closer to the data versus keeping it in a familiar, warm environment. By pushing the first layer of control down to 4 Kelvin, IBM reduced latency and thermal load, but they also introduced a new set of failure modes. Cryogenic chips have different reliability characteristics, and debugging them requires a different toolchain. The lesson is to weigh the performance gains of edge processing against the operational cost of maintaining a more complex, heterogeneous stack. Second, the modular chassis shows the power of designing for incremental upgrades. In many enterprise environments, the temptation is to build a monolithic platform that just works for today's load, only to discover that any change requires a massive rewrite. A modular approach, whether it's swapping out a microservice, a database shard, or in IBM's case, a cooling stage, lets you evolve the system piece by piece while preserving overall stability. The architecture also forces you to define clear interfaces between layers. The 4 Kelvin cartridge speaks a well-specified RF protocol to the mixing chamber, just as a microservice publishes a contract first API. Those contracts become the guardrails that keep the system coherent as you iterate. Finally, the case underscores the importance of cross-disciplinary collaboration. The quantum team didn't solve the thermal problem in isolation. They worked hand in hand with mechanical engineers, materials scientists, and firmware developers. For an enterprise architect, that's a reminder that scaling a system, whether it's a data pipeline, a distributed ledger, or a machine learning inference service, often requires stepping outside the traditional software silo and bringing in expertise from hardware, networking, and even physics. Ignoring those signals can lead to bottlenecks that no amount of code optimization can fix. In short, IBM's redesign of its quantum hardware platform turned a scaling roadblock into a blueprint for modular, low latency, and thermally aware system design. The core ideas: move critical processing as close to the compute element as practical, build modular hardware blocks with well-defined interfaces, and embrace cross-domain collaboration, are directly transferable to any enterprise architecture that is wrestling with the limits of bandwidth, latency, or operational complexity. If you're planning the next generation of a high-throughput service, ask yourself whether the same cold cartridge principle could. And that's your briefing for today. See you tomorrow morning.